Today I will be talking about TensorFlow 2, but my course came out early on March last year where there was no TensorFlow 2, and then it might be that you think it's outdated. But in this course down here, it's this one. I use the Keras API, that is the high-level API of TensorFlow, and this hasn't changed, or almost just very slightly has changed. So all of the stuff that you can learn in my video course still applies to TensorFlow, but at the same time, I converted all the notebooks to the TensorFlow 2, which just barely took me like half an hour, because most of the things are really quite the same. This notebook, so it means it's a mixture of text and code, and the code is executable, and the result of the fractions of code that you execute will be displayed directly in the notebook. Also check out Chris Medman's stream. So Chris Medman obviously explained why TensorFlow 1.x is still relevant. And I guess it is. I'm not quite sure why Chris thinks so, but I would think so that a lot of deployed models are still in TensorFlow 1. But as I said, all the stuff that you can learn in my course, it's basically the same API, because I use the high-level API. So today, because now TensorFlow 2 is there, we can take a different approach. Namely, we look at the low-level API of TensorFlow 2, and from there, work our way up to the high-level API. So this means even if you know the course, or if you still want to watch the course, this could still be pretty useful, because there's barely any intersection. This is the notebook that I'm showing you. So if you I don't know, take a screenshot, or if you're fast, you can type it into your machine, and then you would see the same thing that I'm seeing. So the Colab notebook obviously now is in presentation mode, which is nice, but you can just follow along if you want to. You can follow me on Twitter if you're in that notebook. My Twitter handle is DJ Korthose, which means something in German. It's a special sort of pants. And as I said in the beginning, I converted all of the notebooks that we had in the course. I converted them to TensorFlow 2, and there's a GitHub repository that contains the old TensorFlow notebooks and also the new ones. Let's go through that notebook. And as I said, it's a mixture of code and then not only code, but you can execute the code. I'm doing it now. This is just basic setup of like how big will the graphics be. And what I brought with me is this example. So this is something that we're obviously trying to use machine learning on. And each of these blue points, it's just a sample data point, so to speak. And you have this X and Y axis. And typically it's very hard to associate this to something in your real life, unless I make you think about it a little bit. What could this be in your daily life? So what could be those data points? What could be on the X and the Y axis? What could this actually depict? What could this be? I need you to help me a little bit with this. So I need something in the chat, maybe, that you propose something what those data points could mean and what they are like displaying. So is the matplotlib pragma required? I'm scrolling up. It's not. This is just because I also make this run on my local machine. Telecommander says account balance in quarantine. That's quite funny. I thought that we might find something that's associated to the coronavirus, so it might be. So that would mean X would be time and Y would be account balance, I guess. And I think that's a pretty good thing, and I think we can already just keep that. Why not? Why not stick to this? So this would mean so the y-axis would be account balance. Unfortunately, it's going down. X label would be, let's say, time or days in quarantine, and just calling the whole thing account balance. And as you see, there's some nice features in this Codelab notebook. So you get this like sophisticated kind of UI, but actually when you click into it, sorry, I didn't mean to do this, what I just did. Oh, that was a horrible thing to do. I just messed it up. Try to do something else now. Let's see if I can get it fixed. There's some code behind, and this is just normal code, just Python code, but it's annotated with this kind of stuff. So some parameters. And when you do this, you get this view here as well. Not quite sure what my n used to be. I think it was 100. But I'm also not too sure that it really matters. So this 100 is actually how many data points do we want? And once you change that, this thing gets re-rendered. And it still looks okay, so I think we should be all good. Someone has said that it seems pretty useful for teaching. It is. And it's also very nice to interactively try something else. I also use it if I'm not teaching something, but if I just want to try out different parameters, that's very nice. So as I said, if I change this, for example, you see it's redrawing. You can't see it too much because I removed the scales on the axis, but it does things. I need to put it back to 1, otherwise I'm confused later. So this is the slope of the thing. No, it's -1, okay. And you see once I do this, it gets redrawn automatically. So that's quite nice. Does it work in regular Jupyter notebooks, chiropractical? No, unfortunately not. That's a pity, but there's some things that work better in typical Jupyter notebooks and some things that work better in Colab. And this is one of the things that only unfortunately works in Colab. That's a pity. So there's something else by Nordlicht. Maybe why is satisfaction or happiness? Okay, and that's also quite nice. So on the y-axis, Nordlicht says it could be satisfaction or happiness. And on the x-axis, it could be how long a website needs for loading. And I think that makes a lot of sense. The longer you have to wait, the less happy you are. Also quite nice. So if you have another example in your head, the machine learning approach that we're using, it doesn't mind too much because it just looks at the data points and it doesn't need to have any idea of the domain. Okay, so that's what we are having. Now, I think you already know that what we're trying to do now is we are trying to fit a line through this thing. So we want to know how does it go on tomorrow? After the data points that we have, how does it continue? And typically this would be a linear regression. There's well-proven methods to solve this. Typically you wouldn't use something like a neural network to do it. But our point here is to explain how neural networks work or not to solve this thing actually. So first of all, we make the assumption that this actually is a line. We don't have to do that, but I know the way I generate this thing, it's actually a line. But we can put it into our model. That means into our assumptions or not. First, we put it into our assumptions. So this is our model for this line, and this is the output y. Sorry, this is the account balance. X is the time. This is the slope, and b is the y-intercept. Well, that's where the line that we're thinking of, where does it hit the y-axis. And the slope is how steep is it. So there are two parameters. It's very easy to do in Python. Disregard the rest, don't look at the other stuff. This is the important line here. And you see, I just write it down in Python. Job done. Execute this. This is the input data points. This is the timestamps. And now I can put those timestamps into our model. That's what I'm doing here. And I can plot the outputs. Let's see. And you still see that the original data points, they're still here, the blue ones. But the predictions of our model, it's the red one, it's totally off. So obviously. So it is totally off because we just set the slope to 0, we set the y-intercept to 0, and that's what it's doing now. It just draws a straight line like this. And that's not what we want. So the first thing that we should do is quantify it. How wrong are we? And there's different ways of doing it. And first of all, like the most obvious thing that you could do is like you take the difference between the true value and the predicted value, and you do it for all the data points, and you sum that up. That means if you look at this data point here, this is the true one, the blue one, and the red one is the prediction. And now we are taking the difference between these, and we do it for all data points, and we sum that up. And then we have like any measure for how bad we are doing. It's not speaking to us. That means it's just a number. But that's the first thing we can do. Unfortunately, it comes with a problem, because this difference can sometimes be negative and sometimes be positive. So, in the next step that we're taking, we take the absolute value. So let's execute this. And you see that the absolute value is a little bit different, because sometimes the positive and negative ones, they cancel out each other. And now, this looks pretty high. If you look at the scales, this is between 0 and 1, and they're saying the total like error is 55, but it should be rather between 0 and 1. So what we're doing in the next step here is that we are dividing the sum of errors by the number of data points we're having. So let's do that. And now we're around 0.54, which still is a very bad value, but at least it's a little bit more intuitive. There seems to be a question. Python is surprisingly good for this kind of data. It's hard to understand this, but I see why it is used. I would not necessarily do it like this in Python. It's pretty simple to do it like this in Python, but this is just to make a point clear how you could potentially do it. So if this was your real challenge, you probably wouldn't do it like this, but you could. And yes, Python is quite nice. You could do it in R, and I don't think there will be a lot of like differences. Now we have a measure of like how bad we are, and this is again is just a number, but you could look at it like the average, like how wrong is each data point on average. Now what we're trying to do is bring down the loss, like this number. We want to bring it down to 0. Like it should be a perfect fit. You know, we can't reach that, but this is our goal. And what we can tweak to bring it down is the slope of this line. Again, scrolling up, this is the line, the slope is 0. We can change the slope, so it should go down like this. And also the y-intercept should be different. Obviously, it shouldn't be like hitting the y-axis here, it should be hitting it somewhere else. So those are the two parameters we are tweaking. Let's see. I decided to first do a very naive implementation. And this is how it looks like. We just try it out. It's a little bit like brute force. So we bring M up and then B up. And then we see, does this improve the loss? And if it does, we're committing to it. And if it doesn't improve the loss, we are reversing it. So we are not bringing it up, but it's dead down. And this is what we're doing for like a certain number of times. And this certain number of times is called epochs. Or I call it epochs. Well, everyone calls it epochs, but it could be named whatever. So I'm just doing it for a number of times. And then how far I bring each of these parameters up or down, I call a learning rate. And that's also something that you will find later again. And while I do it in this for loop here, this one, that's how you could do a for loop in Python. I stick in all the data, calculate the prediction, use this loss function that we just created, append that loss function to a predefined area up here, or list, better to say, just to keep it. And then I'm trying to bring M up by the specified learning rate. I'm recalculating the loss. And if the new loss is lower than the previous loss, I'm committing to it. And if not, I'm reversing my decision. And then same thing for B. That is the y-intercept. And that is it. It's a very naive implementation, so you wouldn't use it practically, but this is just to get my point across. I'm running it 500 iterations, that's pretty fast. So the slope that I calculated is minus 0.9, and the y-intercept is minus 0.96. I know it should be -1 and 1, but well, it's hard for this thing to actually find out the right line because it's so noisy. And we can look at the loss over time, like how did we do over the time. And you see it goes down at the beginning quite a bit, and then nothing much happens anymore because we're pretty much as good as it gets. And this is pretty promising because it might tell us that we actually now have this line fitting the data. And if you look at it, it works surprisingly well. I mean, the code is very naive, but it just works. So it's already a working implementation, which is quite nice, right? We do something naive, it works. So far, this isn't TensorFlow. So far, this is just the basic idea of fitting data. You have a loss. You try to bring that loss down by a certain strategy, and then there you are. Okay, so now we already have a working solution, but it might be a little bit harder if we have a lot of parameters, not just one. So in real life, it can be much harder. And then also, we are not trying combinations of each of those parameters. So we're not trying to bring up both the slope and y-intercept at the same time. So there might be issues to it. Now we're going into the TensorFlow part. So what we're doing now is that we are replacing our model, which was a very, very simple model, just 2 parameters. We're replacing it with neural networks. So this is how you get access to the TensorFlow 2 version.